Now, if we could recollect that under our tour of selected classifiers, we started with it. There are so many classifiers. So, but however, we discussed 3 of them. We started with KNN, which is a very popular, very simple classifier that we can summarize as something similar to saying, show me your friend. I will tell you the kind of person you are. That is, if I can be able to know the class that your neighbor belongs to. We have neighbors, we have positive, scatter here and there. So, and then we have one that is unknown. This is unknown. This is unknown class. We want to know where does this one belongs to. So KNN neighbor says, okay, why don't you look into the system, try to see who are the closest to this particular unknown class. So we calculate the distance between this unknown class or unknown sample and all the available samples. What is the distance between them? Then once you have the distance measure for all of them, you arrange them in descending order or in ascending order, as the case may be. So you select either our K, which is number of nearest neighbor, could be 1. It could be, if we are dealing with 2 class problem, A and B, so our K could be 1, could be 2, could be 3. If you are dealing with 2 class problem, it cannot be 2, because if it is 2, there's going to be what we call a tie, because we need to vote. So we look for, if you are looking for K is equal to 1, that means I'm going to look here, who is closest to this guy? So we pick 1, the closest person. Maybe we're going to say, okay, I think this positive class is closest to this unknown class. In that case, or unknown sample, we will classify it as belonging to positive class. That is 1. So sometimes, surprisingly, we do have a problem that K is equal to 1 will be the best parameter value for K. Sometimes also with R3, but majorly between 7 and 11, they are my favorite numbers, either 7, 9, or 11. So we look for 7 closest neighbor to this unknown sample. Let's say we have 1, 2, 3, 4. So if you look at them, this is closer, closer, closer. This is 1 positive, positive, positive. We have 4 positive classes and 3 negative classes. So we're going to classify this unknown sample as positive. We take the majority voting. This was the idea about K-nearest neighbor. We can check out some of the videos we uploaded in this particular category. And then we also move over to, because the K-nearest neighbor is a very simple classifier that we recommend for you if you have a problem. You don't know what it's going to be, because it's very simple, and they call it lazy learner. But then, yeah, sometimes some problems are so scarce, so simple that you need a simple classifier to be able to solve it easily. If you go for higher classifiers or complicated classifier, you might actually miss the underlying structure of the data set. This is something that is unique about machine learning. That is one of the things you need to know about it, is start with simple classifier first. Then from there, you try the simple classifiers, and then you keep moving on to more sophisticated classifier, especially as your data set become many. So the more the data set, then you can then start using sophisticated classifiers. Now, because often than not, people miss this very important point. I've seen people using deep learning to solve very simple problems. And then at the end of the day, they struggle to get like 75% accuracy. The moment I saw this kind of outcome, I said, why would somebody go for deep learning in this kind of application? So we decided to use K-nearest neighbor, and K-nearest neighbor was getting 95% accuracy. See, so deep learning will have cost them a lot of time and so many trouble optimizing and the likes. So, but with KNN, very simple. So we're able to get something more than, that is almost a difference of, if I'm not mistaken, 20% increments in the performance. That is a huge difference. And I'm using simpler algorithm. So this is a very simple thing a very important point I want us to take note. Then we also discussed the decision tree, which is based on frequency. You make the frequency table. I said decision tree is very popular in our day-to-day activity, because every day when you're in your office, you want to solve a problem, we like to break problem down, divide and conquer. This is an idea of decision tree. You see, you divide the problem into two. Should I go left or right? If you go right, then we divide it at this point until you get to the final solution. So it's also very simple. And one of the advantages of decision tree, especially when you have clients, you want to explain your model to your client to increase their kind of confidence. So you need something that they can easily understand sometimes. So if decision tree can work for you, better to use decision tree, because one of the advantage of it is that you can easily explain it to your client to get them to carry them along in what you are doing. So if you can use decision tree, why going for one complicated mathematical based system, for example, super vector machine? So where you have to tell them the kind of optimization, quadratic programming, you have to optimize this and that. How are they going to understand you? So in that case, decision tree works for you. Why going for more complicated options? So this is advantages of decision tree, and so many advantages also we already discussed when we were discussing this particular classifier. And finally, last 2 weeks, we discussed the Naïve Bayes classifier, so which is based on probability principle. So here you are going to calculate the probability that it also has frequency-based system. You are going to calculate the probability that a particular unknown sample belongs to class 1 or class 2. So if one has probability of 0.7 and the other one has probability of 0.3, for sure, we're going to push it here. We say, okay, it belongs to this class. And also, it's probability based. It can still be easily also explained to people better, in a better way than a couple of other more sophisticated ideas. So we discussed this extensively last time, and I remember where we stopped was the Naïve Bayes was the last one. If you remember, we discussed Naïve Bayes. So that was the worst thing with the last one we demonstrated, show us examples and how to solve the zero case problem if you have a sample that has 0 value. And finally, we discussed the applications, because each of them have sometimes unique application area, especially Naïve Bayes. That's why I'm mentioning it again. It has unique capabilities that very fast, it's very, very fast. In real-time application, you can always quickly deploy it. If you have multi-class problem, you see, usually the more the number of classes, the lesser the accuracy you are likely going to get. In most classifiers, if you use a classifier to solve like 2-class problem, yes or no, it gets maybe it got like 95% accuracy or more. The moment the classes become like 3, so I have students who fail, I have students who does not fail, and I have students in between, medium. Maybe you have medium class now. It becomes 3 classes problem. From 95, the capability, the accuracy could degenerate to 85 or even lesser, because now the classes are many, and we have problems sometimes that the classes could be as high as number of alphabets. Imagine I want to do character recognition. I want to recognize character in Yoruba or in English alphabets. You can imagine the number of classes you have, because every alphabet is a class now. So when the number of classes are many, Naïve Bayes could be a very good option for you to quickly look at. It has been reported to have this kind of capability to deal with it. We are not saying it's the best for multi-class problem, but it has very good reputation. When your classes are many, go for it and see what you can get. I mentioned it very clearly. There's no classifier that is better in all situations. It depends on the data. And that's why I kept mentioning this idea, this is my own principle here. Let the data speak. Let the data speak. So that's why when you ask me, I have a new data, what are the classifier you recommend for me? I say, well, go for simpler one, KNN, Naïve Bayes decision tree. However, no one can guarantee that you are going to get better results. If you don't get better results, then keep trying others. But however, before you declare that a classifier is not working for you, you must have done necessary thing, for example, making sure that the parameters, hyperparameters are optimized. This is very important. Otherwise, you will not be fair to that particular classifier. It's like lying against the classifier. I've seen a lot of students had this, they run into this mistake. So, oh, doctor, this classifier is not good. And I said, okay, let me see optimization. They didn't even do any optimization procedure. I mean, for example, now for K nearest neighbor, you need to check, is K equal to 1? Is it the best for me? Is 3? Is it 5? Is it 7? They just use 1, which is the default value, and they say, okay, it's not good. I said, no, this is not fair. By the time they used 7, they were able to find out that it actually performed better than the other algorithm they were claiming that was better than it. So we have to be fair to every algorithm. So maybe with the exception of Naïve Bayes, that doesn't have any parameter. That's one of the reasons why it is very simple. There's no parameter to optimize. Just put your data in there, it does it, and then it solves the problem. Naïve Bayes also, we mentioned that it's very good at text classification, like spam filtering, sentiment analysis. I believe we discussed this extensively last time. It's often used for this. This is very simple, so it's always good for you to try it first before you start going to other sophisticated method. Of course, recommendation system also, it has often been reported. And then we have this activity, which we suggest that if you watch the previous video on Naïve Bayes, try to solve this problem yourself, try to see how it works mathematically. So you have to check, you can see here, these are attributes, shields, runny nose, headache, fever. Then you want to conclude somebody has flu or not. This is normal flu, not swine flu and not COVID-19 flu. So you have to look at the shield. How many shield? 1, yes, yes, no, no, no. So you have to follow the procedure. These are the training sets. You can see here, these are training sets. And now you are given testing set, only 1. It could be more. So you use this to train. This, based on this, you are going to calculate your probabilities of each of the classes as we did, and the conditional probabilities. And finally, based on those probabilities, you now try to solve this problem. If shield is yes, you calculate it. If runny nose is no, if headache is mild, and if fever is yes. Based on your probability outcome, you are going to have one will be higher than the other. If yes is having higher probability of 0.65 and the other one is 0.35, then we go for yes as our answer. So we demonstrated this last time. So today now we are going to move into Weka. We want to use Weka to demonstrate for us, because I decided to just expose us how we can do it mathematically by our own hands, how it works, so that for those people who really want to go inside it and make some changes, you can actually come up with your own in future. You want to design your own, you feel there's something that are not done properly. Can I make it better? Yeah, it's highly encouraged actually. Of course, this is not for everybody. Some people just want to use the algorithm to solve their problem, maybe as a researcher, and that is okay. Yeah, you don't need to really know exactly all the details of what is going on inside the classifier, in as much as you know the procedures that needs to be taken. And these are the most important, by the way, because these days, it's not even, nobody even encourage you now to say, okay, you want to write your own k-nearest neighbor from afresh. I want to write the code from first line to second line. Except for our undergraduate, we encourage them just to develop them, to be able to come up with their own algorithm in future. Otherwise, there's so many thousands of implementation of k-nearest neighbor you can pick up there. Either you're using Python or you are using any other machine learning medium, or to run your experiment. They are all freely available. Most of you are aware we are in the world of open source now. That is the latest open source software. Gone are the days somebody will write the software and say you want to sell it. So the open source are so big now that people write things and make it available for free to use. So you're always free to pick up any machine learning libraries of your choice, depending on the problem you want to solve, and then use it. Now, so moving on. Now let's look at a problem. We described it maybe before. I hope you can see I'm showing you an Excel file. Can you see the Excel file? I hope yes. Okay, thank you. Yeah, This is an Excel file, so let me try to make it bigger a little bit. Yeah. See, this is a data set. It's about chronic kidney disease example. So we have the class here. These are people. This is a patient with chronic disease confirmed. No chronic disease. No chronic disease. No. Yes. No. Yes. These are the attributes. There's the bony value. There's the creatinine value, and the red blood cell count. Actually, that is A. So based on this value that are taken for each of the patient, so we want to see how far can our classifier be able to identify someone that, oh, this person is having chronic kidney disease or otherwise. So you can see here we have several values. Now, this is not a big data, but this is at least acceptable, considering that data sets are usually very scarce. 238, we have 237 samples. So distributed between yes and no. So my data now is in Excel. So of course you have to store it in when you store your data, remember it's going to be in CSV file, CSV. Don't store it as the classical Excel. It will not be detected. Weka will not detect the normal Excel file. You have to store it as CSV, delimited. You see, you have to select the option you want. There's the normal Excel file here and so many other format, but you use the delimited CSV, and then you save your file appropriately. So this file is saved. So now it has 3 attributes. Let's see the 3 attributes. There were many attributes for this data originally, but these attributes were clean. Some of the relevant ones were removed. These are the best 3 attributes that were identified for the sake of the research that was used for. But just for the sake of demonstration, let's assume this is the data set we have originally. Now you open your Weka. Remember, this is a Weka. So you click Explorer. When you see Explorer, so once you click Explorer, so then it will open for you what we have here. Now, see this, it will open for you what we have here. So once we have the Explorer ready, now you can see here, this is pre-processing. Pre-processing, we discussed this. This is where you're going to bring in your data from your file. So there's classifier here. This is where you select your classifier. You can see every other thing is gray out. You can't select anything again because there's no data. Once you import your data, everything becomes activated. Then you can use any of the options. And loading your data, you can take your data from file, you can take it from URL. Sometimes your data set is online on a website. Weka has that capability to take your data from online. It can be a database, you want to open a database, and sometimes you don't have data, you want to generate data. It can also help you generate fake data. So maybe just to practice. So we have our data ready. So we click the open file. So I have my file in the appropriate folder. So inside my document, I think I call it Weka. Yeah, Weka experiment. Yeah. So you can see here, it cannot see anything there in the Weka file. Why? Because here you can see my file type. It's looking for ARTFF data file, which is the original data file that is recognized by Weka. See, if I save my data from Weka, then I can ask it to save in that particular format. But many people use Excel. There's one of our videos, I can refer you to that, where we discuss how to load data from Excel. Because many people face issue if you have to load data from the text file that is recognized by Weka originally. It takes a lot of time and very technical to prepare that file accordingly. So just load it through Excel, which is CSV option, and then you can convert it. If you want it back in the text file by Weka, you can easily save it from Weka. So you have to save this option here, check this option, tell it to CSV. You can see options there. There are different options you can use to bring in your data. So we say CSV data, then my data is here. So I open the data. Now, the data set is open already. You can see these are the attributes. These are the attributes. The first one, the second one, and the RBC, and this is the class. And then we already explained it earlier. you make sure that the target class must be in the last column. If it is in the last column, automatically it will be open for you and placed as the class here. You see, it will be identified as the last one. So if you put your target class as first, then you have to manually specify, because you might confuse weaker, because weaker is going to take the last one in this column as the one you want to predict. That's why I always recommend that make sure your target, your class, is in the last column, so that once weaker brings it in, it will assume that this is the predicted class. Otherwise, you have to manually specify that before you go ahead with your classification. Now, having loaded our file in, so you can check any of the file. You can see here, it's telling us, you can see the minimum, the maximum, the mean, and the standard deviation of that column. You select the second one, same thing, you select the third one, same thing. When you select the class, because the class is categorical, it's yes or no, Y or N. See, so you're going to see Y, N. So in that case, it's going to tell you how many years you have. We have 111 patients with chronic kidney disease, and there are 126 people without chronic kidney disease. So, which is good. There's a little bit of imbalance, but the imbalance is negligible. See, 111 to 126, that's a difference of like maybe something like 15, if I'm not mistaken. Yeah, something like 15 different. That's still fine. However, when you start having one of the years is like 20 and the N is like 170, that is a big difference. We call them the imbalance problem, which need to be solved using the different method of solving the social problem. But however, for this kind of difference in the number, it's acceptable. This is still okay. So now we have our data, everything is set. The next thing you can see here now, these are activated. So you now go to whatever you want to use. Let's go to our classifier. We want to demonstrate the 3 classifiers we've been describing of recent. So classifier. So once you select the classifier, you choose here. The first thing also, we already discussed it. You have to specify how you want to break your data down, which is very important. So am I going to use cross-validation or percentage split? I can use percentage split, in which case I want to break my data into maybe 70% for training, and the remaining 30% will be used for testing. And if I want to use cross-validation, I can specify that I want to use 10-fold cross-validation, or I can make it 5-fold if my data set is not many. That's fine. Like the data set is not much, this is just 2 something, I can use 5-fold cross-validation. However, to make it faster, usually cross-validation takes a little bit of time because it's going to be running the experiment. Every experiment will be run 5 times and the average will be computed. But for percentage split, just divide my data into 2, 70% for training, and the remaining 30% is going to be used for testing. Usually this is faster. So we can start with this. Now the next is you go here and select the kind of classifier that you want to use. Select the classifier you want to use. Here are the list of our classifiers. You can see here the list of classifiers. And then you can see here, this is our friend. Maybe you start from our friend, Bayes. You can see Bayes here. So you click it. You can see different one because we told you about different type of Bayes. You have Bayes multinomial, Bayes multinomial text. If you are dealing with text, if you are dealing with text files or text data cells, we have multinomial, we have Bayes net. So we are dealing with Naïve Bayes. So let us select our own Naïve Bayes. We're going to select this one. So now, having done that, the next thing is, this is where I was talking, this is what I was saying. You can see here, it automatically selected as the class. See, this is what we want to predict. So if you don't arrange your data in Excel to make this to be the last class, maybe the class to be predicted is here in first row. I have to manually specify it here. I have to select it here that this is my target class. Because this here is automatically select the last one in the column, which is here. So let's pay attention to that. It's not compulsory that your class must be in the last column, but I recommend this so that you don't forget. Because if you forget to do that, then you'll be predicting the wrong value. You are using the wrong target as the output, which means all your experiment will be wrong. People make this mistake. So that is why from your data preparation, make sure you don't put yourself in a place to make such mistakes. So now let's move on. So since it automatically selected class as our target, now the next thing is you click start. Start means run my experiment. I've selected Naïve Bayes. You can see something unique here. Naïve Bayes has no hyperparameter. If it has hyperparameter, you will see the list of hyperparameter listed here, as you are going to see for k-nearest neighbor later on. So there's no hyperparameter here. So if you click here, it shows you. These are just simple settings. They are not hyperparameter per se. Now, so I run the experiment. Here we go. Oh, so this is the results. You can see here. This is Naïve Bayes. You can see the now this is the output. Evaluation of test splits. Now pay attention. The result here is the evaluation on the 30%. You see, evaluation on test splits. This is what is showing to us. Because like I said before, the most important is the testing set. Pay attention to that. The most important is the testing set. So it's showing us the evaluation on the testing set. I know somebody will ask me, what about the training set? If you want to see the training set, you need to go to more option, go here, more option, and then you have to say output model for training. You can see here, output model for training split. But then your window is going to be full of both training and testing. See? And then you can also even output the file to an Excel. If you want the output predictions, you want to show the prediction there, it can also show it to us. Now, let's look at the result quickly. You can see that correctly classified instances, 67 were correctly classified. See, because when you find the 30% of 237 data, this is the testing set. So 67 were correctly classified. There were only 4 mistakes, which means we have 94% accuracy. See, so these are other measures that we'll be discussing later on. And this is what we call the confusion matrix. You see, 35 classified as that, A, as A, then this one is, this is yes, A is yes. A means chronic disease, N means no chronic disease. So these are correctly classified people, 35. These are people who are not having chronic disease correctly. These are the 2 mistakes. 3 is a mistake, this one is a mistake. This is false positive. False positive means 3 people are classified to be having chronic disease, even though they don't have chronic disease. See, we have this kind of situation depending on the problem we are solving. Now, if we want to see more results, like I mentioned earlier, just go to more options. Go to more options. I want to see the result. You see, output shows me the result. So we can select, okay, you want the result to be shown. I want it to be shown in plain text. Show me the result in plain text. So then I have to run my experiment this time around. You can see here you are going to get more. You can see here it's showing me more results. See, it's showing me more. These are the instances. This is actual. This is the predicted value. So you can compare how we got the error. The actual is no. The predicted is no. No, no. The predictor is no, but it is yes. This is mistake number 1. See, mistake number 2, mistake number 3, mistake number 4. So when you show the result, you can be able to see actually where our model made mistake. So this is using Naïve Bayes to classify this simple chronic kidney disease data set. Now, and if you want to see the output for training, you just check this one, like I mentioned. Output model for training, check this one, okay. Then you have to run it again. In that case, it's going to show you the result for both training and then the result for the test. It's going to show you appropriately, and that's why it's going to be more depending on the problem actually that we try to solve. Now, the next thing now, let's also look at k-nearest neighbor. Let's look at our k-nearest neighbor. If you want to see k-nearest neighbor, you go to Lazy classifier, under the Lazy classifier, Lazy. So it's called IBK. IBK. You can see when you put your mouse on it, it will show you some description. IBK is K nearest neighbor classifier. It can select appropriate value of K based on cross-validation and whatever description. So I click it. So the same data set, we are running using 70% for training and the remaining one for testing. So here we go. Now, see, you can see here that in the testing set, evaluation of the testing split, something happened to the K nearest neighbor. You can see that the mistake increased by 1. From 4, it became 5. And then you can see the accuracy goes down, 92.9% accuracy or 93% accuracy. So, and this is you can see here also the confusion matrix. There are 3 from this side, 2 from this side, making 5 mistakes. But for K nearest neighbor, I want you to take note. There is something here. You can see here, unlike Naïve Bayes that has no hyperparameter, this one has hyperparameters. K, you can see K is set to be 1. And also, there's the Euclidean distance that is used. So we can change these 2 parameters as we wish. See? So you go in there, this is the default value. Let me share my K, number of nearest neighbor, number of my friend you want to use to determine who I am. Let me make it to be 3 now, because we have 2 classes. When you have 2 classes, you cannot use even number to avoid tie, because it's voting principle. So 3, okay, then I run the experiment again. You can see that when I put it to be 3, the accuracy increase. We only have 4 mistakes now, 4 mistaken prediction. That is just using 3. Okay, let us go further. Let me go further to 5. Maybe we gain some opportunity and get it better. This is called parameter optimization. You can see now that even at 5, something went wrong. The prediction accuracy actually goes down. This is why I usually tell people you can have an Excel to plot what you have. At 1, it was 92.9. We increased it to 3. It became 90. It increased. Then we increase it to 3. It decreases again. So we can see that we have a curve that goes up and then comes down. Then I will select the one that gave me the maximum. It means for this problem, perhaps my best value is 3. So I'll keep it there because this is one that is giving me the best result for K nearest neighbor, IBK. So I run it and keep that one. This is giving me better result, 94% accuracy. However, there's still one hyperparameter we didn't change, which is the nearest neighbor search algorithm, that is the distance measure. What is the distance measure that's going to work for us? You can see here we have Euclidean distance. So I can change it to shape distance. I can make it to be Manhattan distance. What of Minkowski distance? Let me take Manhattan distance. Maybe it will make it different for me. Who knows? Because let the data speak. We don't really know which one we work. Okay, here we go. You can see that Manhattan brought it down to 92. It means that's not the correct option for me. So I go in once again and I try to take it back. Okay, let me try, maybe shape distance will work for me. So here we go again. We run it. Shape also put it up. You can see the same thing like the first one we had, Euclidean. So we keep playing with it, changing this parameter until we got parameters that will give us the best possible outcome. This is what we call parameter optimization that I was explaining earlier in this lecture. It is very, very important. If you use a machine learning algorithm or classifier and you refuse to do the optimization of the parameter, then you are not being fair to that particular algorithm because you declare it as not being fit for the work. Meanwhile, you are the one that is not doing the right thing. So those are the 2 hyperparameters actually we set for IBK. So you keep playing with them until you got the best. And if you like, you can also try more, 5, 7, but usually once you see it go up and then goes down, then you can stop it. See? And the last but not the least, we are going to look at is the third friend we have covered, which is decision tree, if you remember. So you have to go under the tree. Remember, this is for Bayes. Under lazy, you get IBK. Then you move to tree now, decision tree. We want to demonstrate decision tree. So this is tree, decision tree. There are so many decision trees that have been developed. So you can see here, we have decision stump, we have Huffington tree, we have G48, we have LMT, random forest, random tree, reptile. Some of these, for example, random forest is a special version of decision tree. It is an ensemble, actually. It is ensemble. It is, when you say it's decision tree, a tree, like we used to say, a tree does not make a forest. We know this statement. A tree does not make a forest. So when you see random forest, something should tell you that, oh, this is a forest. It means there are many trees there. And that is what they implemented there. Random forest is combination of several decision trees developed randomly. See? So, you know, in our decision tree, we try to look for which attribute is the best attribute to start with. Before we start, we said it has a way of selecting the best attribute using the information gain. If you remember that, yeah, that is the original decision tree. But some people now say, okay, can we develop random decision tree? Don't choose the best attribute. Let this attribute start, let another attribute start, let another attribute start. Because the idea of ensemble is we want things to have different hypothesis function so that we can combine their voting power to get the best result out. That was how random forest came to being. So they developed different random decision tree that were built randomly rather than using information gain. No, they didn't use information gain. They just built it at random. We're going to use attribute 1 to start. Next time, we use attribute 2 as the starting point. Next one, we use attribute 3. Then they do that and build several decision tree. They bring them together. This is what we call random forest. It is under ensemble of classifier, which we earlier also covered. We will also have the opportunity to come back later. We can check the video out on ensemble techniques. Now, however, for the simple decision tree, the one we discussed, we are going to go for what we call the J48. Is the latest and the very popular among the decision tree implementation. Like I said, there are so many implementation of classifiers. You can implement yours, actually. Based on your understanding, you go and implement. You can even improve upon it. Now, so the popular one is known as the J48. This is the simple one, so that we actually describe. So it is the, now, so I selected J48, and then it has very few parameters you can play with. You can see one is set to 0.25, the other one is set to 2. So because this is how you know in Weka. Someone asked me, how do we know the hyperparameter? Hyperparameter will be specified here. The moment you select the classifier, they will display the hyperparameter in front of it so that you don't just go making random selection of the parameter to optimize. If I click it, you see several parameters. These are just parameter, not hyperparameter. And I think I've differentiated between these. Hyperparameter, they are the parameter value that if you change it, they have direct implication on the classifier. But other parameters are just value, for example, number of decimal places. Look at this parameter, number of decimal places. We don't really care about the number of decimal places. This is not something that will affect our algorithm much. However, if we change those ones that are, that's why only 2 are identified here, even though you have several parameters here. In computer science, we use lots of parameters. And parameter is a means to pass information to the function you want to implement. However, when we talk of hyperparameter, these are those ones that will affect the algorithm, the machine learning algorithm exactly. So I hope we take note of this kind of explanation. Now we have selected our J48. Now it's time for us to run the experiment. We are still using the same 70% for training, 30% for testing, and the same data. Start. You can see here, the performance goes down a little bit, so 92.95%. So then it is time for you to go to hyperparameter, try to play with it. You see, this is one of its confidence factor. See, the confidence factor is there. First of all, try to change it. It's 0.25. Can you change it to 0.5? See and try to see if it's going to make a difference. So you run it, it doesn't make a difference. So you keep playing with the values, and then also this second value until you are able to get the appropriate parameter values that work for you. Because when you, with what we have done now, it's like we've compared like 3 classifiers on a particular problem, and that problem is prediction of chronic kidney disease. So we want to see which one is better than that. You can see the three of them are all ranking in the same, around the same area. So maybe by the time we optimize the parameter for G48, we might be able to get better result. If finally we got stuck at 94 or 94% accuracy, which is the best we are getting for the three of them, then we try other things. Maybe we can do feature selection. We can discuss this later because of our time. See, we can go to feature selection actually. So we go back to pre-processing. I can remove some feature. Maybe if I remove this feature, maybe I can get better result. Who knows? See, you can actually remove feature. We can try to see how is it going to work. We have feature selection. You can see here, select attribute. And there are several methods we can use to select the attribute. So if I delete a feature, I remove some feature, how far can I improve my result and the way it goes? But let's stay with the normal feature for now. So this is how we can demonstrate the use of J48, which is decision tree types, also Naïve Bayes, and also the k-nearest neighbor. These are the three simple classifiers that we've had a tour of them. And these are some of the ways you can actually apply it. So you look at your own area of interest, get your data set, open your wiki, and try to play with it as we have done and see what you can come out of it. So I think time is not on our side, so we have to call it a day at this point. So thank you very much for listening. So wish you all the best. If you have any question, we take a couple of questions before we leave. Thank you very much. Assalamu alaikum.